Oh, there we go.
Not like you.
Cool. All right. Well, let's kick things off. Evening, everybody. Large number of us here in the online amateur radio community. We've bought a NinoTNC kit as part of this ongoing series of projects that we've got going on, particularly around packet radio. So for those who don't know, there's probably a full spectrum here. Packet radio, it's a very well-established data mode. It's been around for a few decades now. These days, most commonly it's applied to APRS, position reporting. That really only scratches the surface of what's actually possible with packet. One of the fundamental building blocks of packet radio is the TNC. That's a terminal node controller. It's a specialized piece of hardware that acts as your interface between your computer and your radio. The NinoTNC, it's a modern day TNC, and creator of the NinoTNC is Nino, that's KK4HEJ, very kindly has joined us this evening to give us a bit of a talk on the development and use of the NinoTNC in practice. Hopefully we'll be joined by Tad, KA2DEW, a little later on as well. So really, Tad, sorry, Nino, over to you. I think just one question, actually. If people have questions while you're talking, would you prefer them to hold on and wait, or would you prefer them to give them while you're talking?
Oh, yeah, please pipe up whenever you have a question. We'll just we'll sidebar and answer the question, maybe go down a new path of conversation. I have a few things that I'll talk about, but if anyone wants to steer the conversation, I'm happy to go that direction as well.
Nice, appreciate that. Well, once again, thanks from all of us here, and take it away.
All right. Hi, everybody. My name is Nino call sign KK4HEJ. I live in Northern Virginia, United States, about 30 miles to the west of Washington, D.C. This project, the NinoTNC, it's been around in its current form probably for 5 or 6 years. And by current form, I mean from the early prototype development in wire wrap, which I still have hanging around before we started to manufacture some circuit boards to put this thing to use. But it all started actually, I would say around 2011 or 2012. And I got interested in the idea of working on a little hardware project that takes advantage of some of the technologies that are available at that time in the early 2010s to integrate more processing power into a small peripheral device to maybe bring packet radio back as something that I remember fondly from the early 1990s, and really just see where it goes from there. At the time, the radios that you could buy, and I don't think you could even buy this one 15 years ago, but this is a THD74 from Kenwood. It's pretty expensive. It does 1200 baud audio frequency shift keying packet, as well as 9600 baud frequency shift keying packet. Both standards designed in the 1980s and probably based on development that was done 5 to 10 years before that, but are prolific, and the small remaining use of packet radio in the early 2000s and 2010 was certainly primarily 1200 baud AFSK Bell 202 tones, just like it was in 1984. So why did I decide to build a TNC? I'm not an engineer by employment. I was educated as an engineer back in university a long time ago, but I haven't worked as an engineer professionally. It's a hobby. I thought it would be an interesting challenge to see if I could dig up some engineering skills again and make something really that I wanted to use. And that was something that would be connectable to my computer with a USB cable rather than a traditional serial cable, and tinker around with higher speed modes than 1200 baud. And really, the origin of the modem was my motivation to make 1200 baud packet go away, which I don't think I'll be successful at doing. But at least make 9600 baud packet, which was discussed in the 1980s by G3RUH, which is the creator of the standard modulation profile that's used for 9600 baud back in the 1980s. And he made some modems that were sold in the 80s and 90s. So that was my goal: make something cheap with very little or a very small amount of specialized hardware, hopefully only the circuit board, that would do 9600 baud packet, and sort of pull that mode, 9600 baud, out of the mystery or the dark caves of impossibility. Because when you read old websites about how to do 9600 baud packet, you'll very quickly read and absorb some opinions and some perspectives that it's really hard to do. It's very fragile. Even in the manual for this radio, this modern radio, they give disclaimers about how 9600 baud packet takes 10 times more power for the same range as 1200 baud packet, which it's true. It's a faster mode. There's less energy per bit, so there is some degradation of range, but it can be a very usable mode, that fast mode. All right. So I'll go a little bit into the development of the TNC as it exists now. And after I did that wire wrap board, actually before I did that wire wrap board, oh, my screen just changed. You guys still see me? Yeah, okay. I got in touch with Tad because I was working on something else. And here's what I was working on. This was a 9600 baud data radio that sat on top of a Raspberry Pi. I worked on this in, I don't know, 2012, 2013, 2014, maybe. It's nothing special. That module there came from AliExpress in China. It's a pre-made module with a single chip radio on it. It's got a PIC hiding under here somewhere that is running some of the very early vestiges of the TNC code that's evolved into what's running the modem today. And the idea was you just plug this into a Raspberry Pi and you've got a 70 centimeter 9600 baud data radio at 10 milliwatts or 100 milliwatts, whatever it is. It's almost useless, but an interesting proof of concept. So this got Tad and I talking. This is how I found Tad. I found his website, the Tarpon Network, Terrestrial Amateur Radio Packet Network, and said, hey, I've made this thing. Maybe you could try it out on one of your links and see if it's worth a dang. And I don't think we ever actually deployed that thing. Tad can correct me later. But shortly after that, we started talking about the possibility of, ditching the single board, single chip radio for now, and making a modem, a TNC, that you could actually hook up a radio capable of 9600 baud. And so that's where we went. The enabler, the technical enabler in all of this is a certain line of microchips, DSP processors. It's the DSPIC 33 EP series. These are really great little chips. They're some of the few DSPs you can still get in a through-hole package, which is really convenient for the basement or garage experimenter. Not exactly necessary for inexpensive packet radio, but it's where we are today. We could go surface mount. There is a project going on to put the TNC on surface mount by another party. But we found this chip and it's fast enough. It's about 70 million instructions per second. It's fast enough to do some pretty fast sample rates in and out of the chip and do a little bit of processing to enable 9600 baud frequency shift keying packet. Now, the trick with 9600 baud is you have to have a radio that has the capability of getting 9600 baud in and out of the radio and a wide enough intermediate filter bandwidth to pass the modulated signal in and out of the radio through the antenna. That's a fairly small number of radios that you can buy off the shelf. most of the 9600 baud radios deployed in the Tarpon network, and there's actually a lot of 9600 baud links in use in the Tarpon network, are using commercial data radios secondhand from eBay. The New Zealand manufacturer Tate makes a couple radios that are very good for wideband packet radio. And there are a couple more that we can use at 4800 baud. The trick with fast packet radio, now I say fast, 9600 baud G3 RUH modulation, which is pure frequency shift keying. My TNC uses a little bit of Gaussian waveform shaping to reduce the transmitted bandwidth, but it's essentially frequency shift keying. You have to have the ability to make a nearly DC frequency response connection to your radio, in and out of the radio, both into the modulator and out of the discriminator. So that narrows down the number of radios that you can actually use traditional 9600 baud packet with. And we can talk more about that sometime if you like, and which radios we like and how we use them. So you don't see 9600 baud very often. What we learned through making the TNC, which was originally a 9600 baud AX25 KISS, keep it simple, TNC, is that it's very possible to make useful line of sight radio links at 9600 baud with off the shelf secondhand commercial gear that's not that expensive. And it's pretty fun because it's significantly faster. It's a little bit more pure of a modulation mode, right? You're modulating the frequency of the transmitted radio signal rather than modulating the frequency of the audio being used to modulate the frequency of the transmitted radio signal. So technically a different form of modulation and demodulation. Interestingly, much easier for the DSP processor to encode and decode a frequency shift keyed signal over an FM link than it is for the DSP to work with audio signals, simply because the waveform that comes out of the radio is essentially a demodulated bit stream that you can slice and recover right there from the discriminator of the radio, which you can't do with audio frequency shift keying. Okay, so that was the motivation for the project. Hey, is it possible to bring 9600 baud packet out of the dark ages, out of the mystery of, oh, it's only for the wizards and the engineers to figure out how to make these quote fast radio links? Yeah, it's possible. It's pretty easy. You just have to have some of the right gear. Then as we deployed some of those links in TAD's Tarpon network, the terrestrial amateur radio packet network in North Carolina, we started wondering if we could expand the capability of the same device, this chunky looking green board, the first generation of the TNC that was actually deployed. I think we made 10 of these. We just do a little software update on the chip and use it for 1200 AFSK, audio frequency shift keying as well. And the answer was yes. And right away, after a few dozen hours of coding, we were able to encode and decode 1200 baud AFSK signals. There are a lot of good references out there on the web for anyone, trying to understand how to modulate and demodulate those signals. The code for Direwolf, the sound modem open source, is all out there. You can read through that. This chip is not fast enough to implement all of the methods that Direwolf uses to demodulate audio signals. Direwolf runs on a Linux or a Windows PC. A host computer probably has access to hundreds of megabytes of RAM and probably gigahertz processing speeds, right? We're very limited on the processing power inside the DSP. But that doesn't mean that we have to give up on a significant amount of performance. The latest firmware in the TNC demodulates very well in all modes. It's almost as good as Direwolf. It's not as good because Direwolf's using floating point implementation and more complex adaptations to equalization of the audio channel. So it has a little bit of a benefit there. However, as a standalone device, if you want to just simply plug the TNC into a radio, then plug the other end of the TNC into a computer, I think that using a separate TNC is much more convenient than using a software implementation on a host computer, which is another reason why I get a kick out of working on the software for this TNC. All right, so that was the progression of, hey, I'm curious about radio. Let me tinker with making a data radio to, hey, let's tinker with high-speed packet modes, quote, high speed, to, hey, let's see if we can together come up with a product that's actually useful to sell to people, and not to sell to people in order to get rich. This is purely a hobby, and that's kind of what keeps it fun. We price the TNCs at the point where we can keep making TNCs, and we try to get other companies and other people to carry as much of the burden as possible, which is why we don't buy any of the parts. We have folks go out to their retail part suppliers to get the kit parts. And if those retailers are making a profit on the kits, the parts that they sell, that's great for them, because that means we'll be able to go back there and keep buying the parts from them. We have the boards, the PCBs manufactured. Right now, they're being manufactured by Seed Studios. I buy the microchip DS picks, usually directly from the microchip factory. Once in a while, I'll have them program them for me. Sometimes I just program them here in my workshop before I send them out. We can talk about the supply chain issues some other time, but it's been really hard over the last year or two to keep the silicon in stock in the basement workshop. So we'll go a little bit more through, and please, if anyone has any questions or wants to make comments, just pipe right up or drop a little note in the Zoom message, and we can go from there. But I can go more through the development and evolution of this thing, right? So this was the wire wrapped version. There was actually a breadboarded version that I made just before this, but breadboards don't really survive. It's been 3 moves or 2 moves since then. And I found this in the bottom of a cardboard box. It's got the processor hidden in there. And I like to use wire wrap as a development technique because it's easier to change than soldering wires down to a PCB. You can just unwrap the board and rewire it. The TNC itself consists of a single op-amp chip and obviously the microchip part that's doing the processing, and a USB bridge. All of the features on the TNC have gone through evolutionary changes. The first version that we made more than 10 of was, we called it R2, or sorry, A2. It's this yellow-green board. It's kind of ugly. And Tad was very instrumental in helping me figure out where to place all the connectors and the lights. And you'll see that those change in the different generations of the TNC. But essentially, the DS pick is acting as an A to D, sampling the incoming audio, and it's acting as a digital to analog converter. However, if you look up the part number, the DS pick 33 EP256, you'll notice that it doesn't have a built-in DAC. So we're using pulse width modulation with a carefully designed low-pass filter around that op-amp in order to integrate the pulses to create what's essentially a 9-bit DAC. And let's see, I'm going to answer a question here. Do you have any competition for the chip so it makes it hard to buy? Yeah, Tad answered it there, but we're just buying unprogrammed chips from Microchip, and as long as they keep making this through-hole part, we'll keep buying it for the kit. If they stop making the through-hole part, then we will transition to another chip, and I can talk more about that in a minute. Another question. All right, 2 questions. How do you cope with the transmit code? Do you have to publish and then that gets around the license conditions of secret code? Is the coding open source? So the firmware code, we have not released it open source yet. We might release it open source at some point. There's a couple things around that we're just not done thinking through. In terms of license restrictions, the AX25 standard, which is one of the modulation protocols used by the modem, has been in existence since the 1980s, and it's well documented and published by the TAPR group, the Tucson Area Packet Radio Group. They maintain the AX25 protocol specification. So that's essentially an open specification. Along with the development of this modem, I developed a new protocol, a packet layer 2 protocol, which we call IL2P, improved layer 2 protocol, that is also an open specification. And Tad just dropped the link in the chat. You can go read the specification document there. The useful feature of IL2P is that it integrates forward error correction, which is another thing that we can talk about, another 1-hour talk if you want to talk about forward error correction. But the original AX25 specification for packet modulation is error detection only, no forward error correction. So if a packet has an error in it, it's discarded by the receiving modem, the receiving TNC, and it has to be resent, or it's just a gap in the data stream. We do now have forward error correction in some modes in the TNC. I can talk about that separately. But anyways, the TNC itself, the DSPIC, is acting as the processor, the sampler, and the waveform synthesizer with its onboard ADC and the pulse width modulation module in the DSP acting as a DAC. And that's integrated through a 4-pole Bessel low-pass filter. And then it has a little bit more conditioning before it hits the transmit audio pin of the DB9 connector on the TNC. This is certainly not the effort of one person alone. You wouldn't be able to buy these kits if it wasn't for the help of Tad giving me the feedback of an experienced engineer who's been working on products that people actually buy for his whole career, as well as a couple other advisors who've helped us develop different parts of the TNC. All of the linear parts, so the circuits around the op amp, the quad op amp on the board, were advised by N1LTV, and his name is on, or at least his call sign is on the A4R2 board. He's given me hours and hours of advice on how to make better analog circuits and better meet the goals we have for the audio portion of the TNC. Let's see. Question from Simon: is the Raspberry Pi Pico viable? It's through hole, lots of performance, and lots of serial I/O. Yeah, I think Tad's nailed it there. If we, believe it or not, the DSPIC that we're using is extremely capable for what it does. The reason that the TNC right now with the most current firmware can perform anywhere near as well as it does, and I mean in terms of sensitivity in receive in audio modes, is due to the built-in DSP machine code in the microchip part. And most of the firmware is written in C. However, I had to write a small part of it, you could call it the convolution engine, in microchip assembly in order to access the DSP machine code that's included with that part. There are specific DSP commands that do not quite convolution, but multiply and accumulate extremely fast, like 1 cycle multiply accumulates and 1 cycle divisions. And believe it or not, even though the Pi Pico is fast, it's not capable enough to do what the DSPIC is doing on this TNC. There are alternative processors that are faster. For example, we've been flirting with the idea of like, hey, what processor would you use if money wasn't an object for the thing and you wanted to make the highest horsepower standalone TNC that you could? And a year ago, my answer was the ST32 H723Z. So this is a 500 megahertz DSP chip on a development board, the Nucleo development board. And what you see there is just like those funguses that infect the ants and turn them into zombies. I've got it wired into an A4R2 in the place of where the DS pick would go. All right. And I ported the code to the point where only the 9600 baud transmit and receive is working, but it's using a fraction of the available processing power on that chip. And it's got a ton of RAM and a ton of ROM. It's got a built-in USB bridge, serial port emulator, all kinds of advantages. I just haven't spent much time on that right now. I would have to actually dig into the programmer's manual for that part and write another assembly language subroutine to do the convolution, which I haven't done yet.
What's the difference in price?
Oh, that's in single quantities, that's a $15 processor, right? In single quantities, the DS pick is a $4 processor. So, you know, we would pass that on basically one for one if we were able to do that, if we ever develop it to that point. And obviously that's a large quad flat pack. You're not going to hand solder that in your basement. I mean, someone might, but we're not going to sell a kit that includes a large quad flat pack for people to try to hand solder. So we'd have to have those boards completely manufactured and tested. And once you say, I'm going to sell an SMT board, well, then you're also selling a finished product, right? And that has implications for sending things from the United States to Europe. And it has implications for a warranty, and it has all kinds of things that demand that we get bigger than me in my basement and Tad in his attic. All right, I'm going to catch up on the questions here. Let's see. Francis is hoping to use his Pi as an interpreter to give a Commodore 64 access to the TNC. I tell you what, you know, you might not need the Pi to use your Commodore 64. What I would do in that case, if I had a Commodore 64, I would not populate the USB bridge on the TNC and wire the serial lines directly to whatever serial port the Commodore 64 has. And then all you would really need to do is write some lightweight KISS interpreter code for the Commodore 64. And you could communicate directly with the TNC. Or at the very least, you could display packets being received. I don't know how fast the serial ports are on the Commodore 64 or any of those old computers, but it's worth looking into. And
sadly, Jack, I was going to say, sadly, Jack Trammell cheaped out and he didn't include one, but I know the Amiga has a 1200 baud, so that might be the answer.
Well, I tell you what, if someone gets an Amiga terminal going and they want to hook up a TNC to, I will spin a special firmware that has the serial port data rate set at 1200 baud so you can interface it to it. That's going to demand a lot of compromises, but you know, I think that's one of those things that is worth doing just to see it work.
You heard it here first, Francis.
It's so tempting. It's going to be one of those where I just have a weekend and I'm just like, you know what, I'm going to do it. But for first, I'll play with the TNC first.
Okay, here's a good question from Dave. As a non-programmer, what connections are necessary to the radio, 1200 audio, and you mentioned that we had to connect the discriminators to 9600 back in the day. Okay, so if you're going to do, let's just talk about 1200 baud audio frequency shift keying, because that's still a prolific mode, right? And if you think of 1200 baud AFSK as the nature of the sounds that go in and out of the radio, we can separate that from the protocol that is used to modulate the data or encode the data, I think is a better word, which is AX25 in traditional packet radio. It's IL2P in the Tarpon network to use the forward error correction features of IL2P. You could use either connected to a radio using 1200 baud AFSK. So in order to connect one of these TNCs to a radio, you just have to have a connection to the microphone port and the speaker port. So if there's a headphone jack in the back of the radio, you can wire that directly into the radio. And I'm going to see if I can do this special feature here with Zoom. I'm going to use my iPhone camera. Tom, can you still hear me?
Yeah, we got you.
Okay. So here's an example of some old technology, right? But I really like this radio. This is the ICOM 2AT. T means it has a touch tone pad, right? It's got the thumb wheels on the top. This is one of my favorite radios. I've rebuilt the battery pack with nickel metal hydride rather than the old NiCad batteries so that it actually is usable now. So this is what I have hooked up to the A4 TNC on my workbench here, and I'll describe the connections. The 9-pin port on the back of the TNC essentially contains the connections for push to talk, audio in and out, and ground. That's really all you need in order to hook it up to the radio, right? Then you just have to know how the connectors are pinned out on the radio that you have. So in this radio, I think it's a 1/8 inch mono audio plug for the speaker, and one of the smaller ones mono for the microphone. And that's all you need to hook it up to the radio. And I'll give you a demonstration of this radio sending some data to my $600 Kenwood. Let's see if this works. So the radio right now is set to put out about 100 milliwatts. It's running into a dummy load that's about 10 feet away. And my Kenwood is on 145.51. I'm just going to push the button on the TNC. It's going to send out a test tone, which you'll be able to hear. And then when you let go of the button, it sends a self-generated packet. And the intent is for easy diagnosis of problems and just to prove that the radio and the TNC are talking to each other and working. All right, so there, that went through the ether over to the Kenwood, and you can see that test packet that came through. Let's try to stop shaking the camera here. Do another one. You can see it received a packet from KK4HEJ-12, and it's just got a bunch of random ASCII characters in there, right? So it's really simple to connect the TNC to a radio through audio connections. Let me catch up on the questions here. I'm going to turn this camera back to me. All right.
Nino, if you can elaborate maybe just a little bit on the second part of Dave's question, which is around 9K6 and connecting to and from discriminators.
Yeah, for sure. I'll grab another radio as an example. So before we're done with the talk, I'll bring up Tad's webpage where he's got a ton of information on practical knowledge about packet radio. And it's a really good resource for anyone who's just getting started, even if you're not interested in building a Tarpon network with Tad's formula, but he's got a pretty good formula for building a packet radio network. There's a great volume of information there on connecting TNCs to radios and getting them to work. And the entire user's manual and building manual for the TNC is on his packet, his website as well. So this is an example radio that you can do better than 1200 baud with. This is a TK760. It's a commercial radio from Kenwood. You can get these things on eBay. I wouldn't pay more than like 40 or 50 bucks for one. You got to like hunt around for the programming software. I think you can actually use Chirp to program this one. And it's possible to dig into the guts of this radio, find the right places to attach a wire to unfiltered receive audio near the discriminator and nearly unfiltered audio input that has nearly DC response. The problem with this radio is the intermediate frequency filter bandwidth is too narrow on receive for it to receive a 9600 baud waveform. You need about 20 to 25 kilohertz IF bandwidth to do that. This radio will do 4800 baud pretty well though, and there's a setting on the TNC for 4800 baud. So if you are not afraid of opening a commercial radio, there's a handful of commercial radios that you can modify or tack solder a point in the radio to get access to nearly DC response and something that's suitable for frequency shift keying. Okay. Tate, that New Zealand manufacturer, they make a radio which is good off the shelf. However, this one, you have to find this on eBay or secondhand as well. This is the TM8105. This is a 20 watt radio. That Kenwood I was holding was a high power version. I think it's 50 watts. This one's a 20 watt radio, but it's plenty for reliable line of sight links as long as there's not mountains and trees in the way. It has a 15 pin connector on the back of the radio, which gives you direct access to the signals you need to send and receive frequency shift keyed audio from DC with about 25 kilohertz bandwidth. These radios will do 9600 baud really nicely. You do need a programming adapter for them. We've got instructions on how to make them on Tab's website. We also have one of the members of Tarpon who sells pre-made programmers. And you also need the programming software, which floats around on some internet software sharing sites. If you're really interested, get a hold of me offline. We can talk about how to get that. There are other radios you can buy, brand new radios, that have what you'll hear referred to as a data port, which is the connector that looks like a 1990s S-video connector. I think it has 6 or 8 pins on the back. And those radios typically cost over $300, but they have access to the discriminator and the varactor diode input, essentially the modulator without any filtering, right off the shelf, right? So if you're happy with buying a Kenwood TMV71A, or I think there's a brand new Yaesu dual bander that has some access like this. The FT817 and 818 QRP all mode radios have data ports, which will do 9600 baud, but those are 5 watt radios, and you're paying a lot of money for some features you're not going to use. That's the thing about buying all these data port radios. You're typically spending more money than you need to in order to get access to 9600 baud, which is why in the Tarpon network, TAD has typically been using these secondhand commercial radios to get 9600 baud links. Does that answer the question? I
would have thought so. I don't want to speak for Dave too much, but there's some detail. That's good. Thanks.
Yeah, and TAD and I are happy to point people in the right direction if that's the direction folks want to go. I'm going to read through some more of these. Amiga serial port sounds fast. Okay. TAD's dropped a link to the wiring. Okay, Daniel says, so for 1200 baud, you can interface effectively with any radio, even with the cheapest 10 quid Chinese handheld. All right. Yes, the answer is yes. All right. So another reason I love this old ICOM boat anchor is because it's of almost no value to everybody until you hook it up to a TNC. And now it's actually really useful. I use it all the time for diagnosing firmware updates and testing things out. The Chinese radios, I would avoid them, okay? Not because they're from China. However, the features you need for an effective packet radio two-way link include not just frequency response and the bandwidth that you want. You also need to have relatively fast transmit to receive turnaround. I have a bucket of Baofeng's 70 centimeter radios. I'll grab one just so you see what I'm talking about. All right. This thing came from Amazon. It says Alwad on it as the brand. It's a Baofeng BF666. If you've never held one of these, it feels like a toy, right? But it will actually send and receive on the 70 centimeter band. It also has a speaker and a microphone port, which you can connect to the TNC, and it will send packet and it will receive packet. However, if you try to send and receive packet with something like an ARQ protocol that was going to acknowledge a frame and say, hey, I got that frame, don't send another one, the turnaround time is almost 1 second from transmit to receive on this radio. So even if the radio or the modem was sending a super tricky, complicated modulation over the audio port, compressing data and sending really fast signals, you're not going to get any effective throughput because the turnaround time is too long. So they're interesting. They're kind of fun to play with. I typically avoid them. Now, you know, there are some higher end Chinese radios now that are a little more expensive than $11. They may do a little bit better, but I would just say on any of the cheap radios, beware and check out the turnaround time, transmit to receive. But if you had a cheap 2-meter handheld and all you wanted to do was listen to APRS, you could do that. Let's see. All right, I'm going to skip over some of this. Dave says, I did the 9600 baud mod on a Yaesu 70 centimeter. It didn't work. Unlucky. FT6000, that might be one of them that has a data port now. I would have to look it up on the website. That sounds right, but don't take my word for it. Robin says, I did see something referring to Tate offering their programming software. Oh, that's nice. Okay. All right, I think I'm caught up with the questions. Any other questions out there in Zoom land before I start down another rabbit hole?
I'll go with one if that's okay. So, yeah. Given, I mean, you talked a little bit about what's possible given current commercial radios. Given unlimited CPU, but still the limitation of those radios, what's the next limit we're up against for bandwidth in an FM channel after 9K6?
Yeah, so
if any,
you'd have to get out your textbooks on Shannon's information theorem, and the answer is you probably owned a dial-up modem that did better than 1200 baud, or maybe your dad or mom did, right? I'm not sure how old you are. I certainly had a 57.6K modem that I hooked up to my computer and a telephone line, a standard 3 kilohertz telephone line, and was able to browse the internet at 56K, right? What are you up against? You could make more interesting modulation modes that fit in a pure audio channel. And by audio channel, I mean a channel that's been band limited to 300 hertz to 3000 hertz. That is typically the rough frequency response of the audio systems in off-the-shelf radios. And it's something that I'm actually working on. I have a few simulations that I've been tinkering with for an orthogonal frequency division multiplexing audio channel over a 3 kilohertz bandwidth. And in that case, you could just plug that modem into your IC2AT speaker microphone port and get more than 1200 baud. It just takes a little bit more processing. And as you increase the throughput in a restricted bandwidth, you will take some cost in terms of energy per bit, right? Energy per bit of information that you send, which just means the link might be less robust, or you might need more power to get your data through. You can account for some of that with forward error correction, but forward error correction isn't magic. You can't overcome any of the laws of physics with forward error correction. So I do hope in the next couple of years to offer a firmware update to the existing TNC with the existing chip that will do better than 2400 baud through an audio channel. And just so everyone is aware, the TNC that you're going to build can already do 2400 baud using audio phase shift keying of a tone through a completely voice-only radio link, which is a significantly better rate than 1200 baud. We use that quite a bit in the Tarpon network. It works pretty well.
Sorry, Nino, just on that aspect. So theoretically, without having a radio that was suited to 9600 baud, we could achieve 2400 baud if we were just working together quite comfortably.
Yeah, I haven't found a radio that fails at 2400 yet.
Okay, that's cool. That might be interesting.
Yeah, it's pretty good. Now, just so you know, you might find some old TNC modems from the 90s that have a 2400 baud mode. That was essentially the same as the 1200 baud mode, but everything was doubled. They just made the tones higher frequency and change faster. So those 2400 baud modes that use different audio tone frequencies from the 90s are not the same as the 2400 baud mode that I made for this TNC. This is a completely different mode. I'm not aware of another implementation, software or hardware, that uses the same 2400 baud modulation. And all the modulation is phase reversal of a 2400 baud or 2400 hertz audio tone. And I actually I think we have a paper. Yeah, it's called DPSK modulation, published on TAD's website, which I'll show you in a little bit where to find that.
Awesome, thanks.
Let's see, I'm going to read some more questions here. Vic says we have a bit of history in the community of burning things. Yes. Can the TNC be used continuously for hours at a time without hurting it? Yeah, we've had these things plugged in probably for years. TAD has a few in remote locations in his network that have been running for a long, long time. The power draw is pretty low. It's powered by the USB connection to your host, and I believe it's less than 100 milliamps with everything operating. All right. Okay, there's TAD with an answer there. Okay, been talking for 50 minutes, and it's been fun. I could probably talk for another 3 hours in a very uncoordinated and random, rambling way. But any other questions? I'll share another thing that we have going on. So I showed you this is the ST Micro version with the 500 megahertz processor. I don't know if we're actually going to make that, but I will keep playing with it and try to make it work. This is also an ST Micro Nucleo. This is a more reasonable chip. It's about the same cost as the current DS PIC, and it does have DSP. I'm at a loss for words, commands in its assembly language, which I can use for modulation and demodulation. That one runs about 2 or 3 times faster. It's 170 megahertz ARM Cortex M4. It's the STM32G431. It actually has the same amount of RAM and ROM as the DS PIC. So the only advantage on that thing is, well, there's 2 advantages. It runs faster and it has a better ADC. The ADC on the DS PIC is 12 bits. However, we're sampling at between 28,800 and 57,600 samples per second, and then applying a fairly long finite impulse response low pass filter and decimating. So effectively, you're getting a little bit of bit resolution gain through oversampling in the TNC as it exists now. So I estimate there are 14 effective bits of resolution in the data that's processed by the TNC. The STM part that I was just holding has a proper 16-bit ADC, which will be a little bit of signal to noise ratio advantage, a little less quantization noise, which will make it theoretically a slight bit more sensitive. Are you actually going to notice that in use? I don't think so, because for the most part, when we're talking about data over an FM radio, the weak point is the FM radio. There are much more efficient methods of putting information into radio waves than frequency modulation and discrimination on the other end. However, these are the radios we can go buy, and we're not in the business of making commercial radios. More questions on the side here. Let's see. Can you take us through a whistle-stop tour of the build process? For sure. So let's see. So when you get your kit, you'll get a bare board that looks like this. It's a 4-layer board laid out with hand soldering in mind. I will load the web page. It's a good idea, Tad. I'll show it in a sec. And you'll get the DS pick. And Tad, please feel free to turn on your microphone and camera and take over at any point if you like. I'm about to share my screen if I can figure it out. Here we go. Dun, dun. All right. Thumbs up from anyone who can see the NinoTNC webpage.
Yeah, you're good.
All right, great. So tarpon.net/d or ninotnc.org, you can get to this website. This is Tad KA2DEW's website. Tad's put hundreds of hours into documenting this project, as well as all the work he's done to build the packet radio network in North Carolina. There are a few links here. Info, news, and ordering is instructions on how to buy the kit and how to buy the parts, really written as though you're living in the United States. So, Tom, I guess you're heading up the effort to get all the parts coordinated from different vendors.
They're sitting on my study floor right now in 46 bags.
That's fantastic.
So they're ready to go.
That's awesome.
I have to compliment you, by the way, on the way that the bill of materials has all been laid out. That system you've worked it made ordering this stuff from Mouser an absolute joy. So thank you. Yeah,
thanks for the feedback. That credit goes all to Tad and some of the volunteers who help us test out our dumb ideas and make sure it works. So Tad is the documentation genius, and he's the photographer and the writer for all of the things that you're going to read on this website. That's the picture of what it should look like at the end. Why do we offer this? Because quick sanity check before you solder something down. Take a look at the picture and make sure the resistors have the right colors. Make sure the op amp and the USB part aren't swapped. Make sure that you can read the numbers on the op amp correctly. I'll fast forward a little bit. When you're building your kits, there is a step-by-step instruction on this web page that I'm showing you that I recommend and Tad recommends you follow, because it includes intermediate testing that will identify errors before it's too far along to identify the error. I mean, I haven't found a TNC I can't fix. So, worst comes to worst, throw it in the mail to the United States and I'll get it back to you working. I can make these work no matter what.
Even better, find the Stucky that's local that you can deliver it to, because there's certainly talented people. That the trick with any group project is to identify the person who's the good person in the group to do each aspect. And of course, carpenters, machinists, PCB layout, coders, soldering specialists, they're all out there. And the more people you have in your group, the more likely you're going to have a really good one of any one of those.
Very good words, Tad. Thank you.
Yeah, scroll down to the assembly instructions, because that's the trick.
Okay. Okay, there's order the parts. Am I on the right page? Yes, I am.
You are.
This is a quick primer on how to do good soldering. Great stuff here. Again, Tad put all this together. Pictures of the front and back of the circuit board, which you can zoom in on. There's the schematic. It's a very simple schematic. And a description of all the parts and the instructions. All right. So when it's time to build these things, read through the instructions once, right? And then just follow the instructions as precisely as you can, and you will be successful, right? And if you're not, then we can get you successful. I'm pretty confident in that. Tad lays out the order, the recommended order to put in the parts. It's generally low profile parts first before the high profile parts, because it's easier that way. And the board is easier to turn upside down and have stable to solder if all the parts on the top are the same height.
We've got a great question in the chat from Vic, which is relevant to the soldering. I assume soldering rather than overheating in general, Vic. But Vic asks, are there any parts of the kit that are particularly prone to damage through overheating? Take that as excess heat from the solder, I guess.
I think the easiest thing to make ugly would be the 28-pin socket, because you might just melt the plastic. But I don't know if it would become non-functional.
The thing is, nobody's ever done that.
Right.
Out of 2,000 of these things assembled, the things that have gone wrong don't include that.
Yeah, you're probably okay.
Let's bear in mind, this is Vic's third reference to fire in this presentation so far.
That's great.
I've seen his soldering.
Yeah, and it's worth noting as well, we've had offers from others in the community to include in our own just now. Anyone who doesn't feel confident with the building, there's plenty of people out here who can help out locally without having to ship transatlantic again.
Yeah, that's great. It'd be great if you built that network in the UK so that you guys can organically do this. All right, so this is going through the resistors. You can see that's a theme. All the resistors are going in after the crystal. Pay attention to the markings on the small ceramic capacitors. Some of the ceramic capacitors look similar, but there's an 18 picofarad pair, which are for the crystal. And then the bypass capacitors look very similar, but they're 0.1 microfarad. That could be a frustrating thing if the crystal oscillator is not oscillating. It's possible to put the MOSFET push-to-talk driver in backwards. So pay attention to the pictures here on how to orient it.
The level of detail on this is amazing.
Thank you.
Really, really good.
Yeah, that's all
project documented like this.
While we have the MOSFET on, is there any issues with modern radios with the PTT?
So no, all the radios we've tested work with this MOSFET. And believe it or not, we put many hours into picking the right push-to-talk transistor, because we've got folks using ancient radios. We're talking like boat anchors from the late 1970s that require 100 milliamp drain to key the radio. So we were using a silly NPN transistor as the push to talk up until about 2 or 3 years ago, when someone piped up on our email board and said, hey, it won't key my ICOM 8,000-year-old radio. So I found one of these things. I think Tad sent me one and started testing it. It required so much draw, we had to find a better part in order to key that radio. So
we started with the opto isolator.
That's right. Yeah.
And then going to the FET, and then this thing. This actually is, excepting for maybe the USB connector, this has been the biggest chaos in the project.
Yeah. Finding a consistently good push to talk transistor. Now you could do, if we for some reason run out of IRLD 120s in the next couple years, you could use many other transistors and they will be good enough for 99% of radios. So that's not the end of the world. We're really trying to make a thing that's fun to build, useful, and generally usable with whatever equipment you find.
With the least amount of tech support required.
Yes.
The only thing I'd say on PTT, having built one, and this is no fault of your kit, I've got a Wouchon.
Yeah.
And when you ground the PTT, it doesn't actually PTT. It needs about 150 ohms on it, which is nothing to do with your kit. There's something weird in this radio.
Oh man, with a
so
FET.
I found that because
so it worked
perfectly on my Baofengs, worked perfectly on my Kenwood V71, and I'm like, what's going on here? And then when I looked and started playing with it, if you shorten, it won't PTT. You have to leave a little bit of resistance there. So who knows what's going on with that radio?
That's great. Wow. That's great to know. We would love to include that detail in our builders information.
Yeah, so, send me an email. I'll put my email in the chat. I'd love to know about that.
I'll stick it in the groups.io as well. I'll go back and remeasure it as well.
That's fabulous.
Yeah, that's good information. Okay, so here's a good point. Here at step 14, we're putting the voltage regulator in. You can see in the history of these instructions, we've used a 3.3 volt regulator, a 3.1 volt regulator. You guys are going to use a 3.6 volt regulator because that's all that exists in the world right now that fits in that hole. I've read all the microchip documents. I ran one of mine on 3.6 volts for a couple weeks. It'll be fine. If you melt some chips, let me know and I'll send you more chips and we'll come up with some other plan, but I don't think that's going to happen.
No.
The DS PIC is rated to operate from 3.0 volts to 3.6 volts, which means it's been tested slightly outside of those margins and they're accounting for variability in a 3.6 volt regulator. So I'm confident that you guys will have no problem at 3.6 volts and the LEDs will be brighter. No, but an actual advantage of 3.6 volts is you're going to get 10% more voltage swing out of the TXA line, which will allow you to more easily set a high deviation if that's needed for whatever radio you find. We have found some radios that like a little bit more voltage to create proper deviation. Resistor network, it's possible to put that in backwards. Notice that it's got a dot at the common lead. This is a bust resistor. It's just an easy way to bias all of the LEDs that are on the board. So don't put that backwards. You should be able to read the letters from the front of the board, the front being the side with the LEDs. I'm not sure what color your film capacitors are, Tom, but they've been white, they've been blue. They're generally the biggest cubes or rectangles in the bags. They shouldn't be much confusion about the size on them.
I can't remember. I'm not next to the kits at the moment.
Yep. Tantalum capacitors are possible to put those in backwards as well. They are polarized. So just pay attention to the little tiny plus. Make sure that matches up with the plus on the board. Again, Tad has zoom ins here. We used to use different value trimmer pots, which was a potential stumbling block. Now they are equal value, so they should be both 10K pots. So you can't mess that up.
I would like to say thank you for putting in the type of pots where it actually has a cross, because that's easier to use. I used to have to do them for a living in tape radios when the bus services broke the tape radios every 2 weeks. They had the smallest, tiniest pots in the world that were a nightmare.
Yeah, you're welcome. I can't remember exactly why we picked these. I think it was probably durability, and we wanted a right angle facing pot so that it could be adjusted from a rack in the side. Here's another one to pay attention to. We have had one kit built that had the 3300 picofarad transistor and the 1500 picofarad transistor in the wrong places. They're the same size. That'll change the characteristics of two separate analog stages, and they both won't work.
Yeah, word salad. Capacitor.
Yeah. Capacitor, thank you. These are C7 and C10 now. You probably have ceramic capacitors instead of film capacitors.
Yep.
Those pins on the USB connector are fairly close. It'd be easy to bridge those with solder. Important step here, testing the regulator before you start putting the quad op amp in, just so you determine that that is correctly polarized and limiting the voltage correctly.
So obviously, basic multimeter is probably a good thing for people to get if this is your first rodeo.
For sure, I highly recommend that. Very good thing to have. The dip switches will work in either orientation, but I recommend you put them in with the numbers oriented the same as the rest of the silk screen, just since our operator's manual is written that way. Don't know what colors yours are. I can't remember if we're using The black ones are the red ones now, but they have the same footprint. LEDs, you can put LEDs in backwards. So good to take a close look at the leads of the LED and match the pictures here when you're putting them in the board. And Tad gives a little demo on how to bend them.
Whoever came up with that technique for bending them is a genius.
Again, that's Tad.
I built a V3, so these will be my first V4 kits coming now.
Great. V4 has a better analog front end in terms of design. It has the same parts, but they're laid out. They
also,
are better.
The A3 had jumpers that were just really difficult to explain to somebody. Like, oh, did you do this? Like, oh, what do you have to do? You remove a jumper? No, the switch is so much better.
Here's a little description of what the LEDs do. Obviously, that's firmware dependent, and we do, manage the firmware and maintain the firmware. So those are all subject to change.
Yeah, try to make it so that the documents all reflect the most recent released version of the firmware.
Yeah. And Tad, I don't know if I told you this, but remember I sent you a 3.17 update firmware that fixed something. Can't remember what it fixed, but it was the loop test, the loop back test. Remember that was failing 40% of the time.
Yeah.
On 3.16. So I'm shipping 3.17 now, which includes the beta HF modes.
Yeah, we need to document that, the beta HF modes and the test modes that you have to use the test button to switch into. I need to make sure all the documentation is right for that. There's some features built into the TNC that aren't really discussed. The bit error rate test and bit error rate receiver. I need to go through and get pictures of all of that and what it looks like on a dumb terminal and that kind of stuff. Yes, the firmware can be flashed. There's a bootloader built into the CPU, and there's a program on GitHub that we point to, and there's also programs that are on our website. There's an installer that lets you flash installs onto a Raspberry Pi. It lets you flash, but there's a GitHub for getting the program for the Windows. But yeah, there is a limitation on the flashing. Some of the older versions can't be put in on top of a new version, and the new versions can't be put on top of a really old version. After I guess about a year ago, Nino got the bootloader to a state that we've kept since then, and so anything since then can go back and forth. So for beta testers, it's very handy to be able to overwrite the new version with the old version, and et cetera. But there's a limitation to the history because the bootloader changed.
Yeah, and suffice it to say that the new firmware is so much better than the firmware that is no longer bootloader compatible that old firmware might as well just be thrown in the dustbin. The bootloader is one of the more complicated parts of the firmware, and it actually has code that updates itself. I don't know if any of you have worked on bootloaders before, but it's sort of like the Inception movie on determining what state am I dreaming or am I awake kind of thing.
It's sort of like replacing the tile floor while you're standing in the middle of the kitchen.
Exactly.
What was I going to say? If you were to somehow manage to convince the chip that it could no longer run, the tool that it takes to replace the firmware, all of it, from regardless of the mode that the chip was in, that tool is called a pick kit, and they exist on eBay around here for about $40 US. New, they're going to be on the order of $100. I don't know, but only one person has one within an hour's drive, and everybody will be much more comfortable. But anyway, bootloading and crashing the chip and getting it stuck isn't anywhere near as likely as finding a used KA2DEW that has the old chip, the old version in it, and now the new bootloader won't talk to it. So that chip would need to be visited by a pick kit to bring it to new. But as far as the hardware, the chips that we shipped in the very first units are compatible with the new software, and the KA2DEW can run the latest software.
Yeah, believe it or not, you could put the latest software on this one and it would still act like it did several years ago. All right, there's a little description of what the TNC does when it powers up. The rest of this is test protocol that Tad has written out in order to trap errors and identify them and correct them before you say you're done. And it's all really good stuff. And then there's some common troubleshooting here, how to make sure the LEDs are in the correct orientation based on the shape of the anode and the cathode inside the lens.
There are so many features on this TNC for usability and testing that just completely blow away all the prior TNCs. It's stunning to imagine that none of the TNCs made up until now have a light on them that tells you a good packet was received.
Yeah.
Another light that tells you you're overdriving the transmit audio. Or the receive audio, I mean. If you turn the receive volume up too high on your FM radio, it lights a light to say, hey, it's too loud, turn it back down. The loop back feature with the clip leadable connections, they're shown on the picture right now, the TXA and the RXA. You can take two TNCs and connect them nose to nose by clip leading TXA on one TNC to RXA on the other. And you can demonstrate now a packet link from host to host through the two TNCs without having radios. And similarly, if you connect two TNCs across two radios without having any hosts, just have to power the things up by plugging them into a wall wart, now you can prove that your link through the two radios would work. Before you hook up whatever X router or G8BPQ or WinLink or whatever you're running, you've now proved that your link radios work, which is another stunning, seemingly obvious feature once you have it, but nobody had it before. It's really stunning, amusing to me.
Yeah, all good stuff, Tad. I can show a demo of that overdrive indication later if we have time and if anyone's interested. We've gone through a few versions of op amp. We have a list of compatible op amps. It works with a 1 megahertz op amp. The critical feature is rail to rail in and out at 3 to 3.6 volts. So the MCP 6004 is a good one. The MCP 6284 is a good one. There's a couple TIs that work. The MCP 604 we've used and we've deployed. It required a firmware update because it actually has limited, it's not rail to rail input, it's rail to rail output. And we detected this kind of late. So the current firmware will work with the MCP 604 because it offsets the DAC output just enough to keep it within the common mode input voltage rated for the MCP 604. So bottom line, all three of those op amps work, as well as a few others that I have a list of, but we haven't had to use yet. The USB bridge is a microchip part. It's the 2221 or the 2221A. The A model is newer. It supports a higher maximum rate, but it doesn't matter because we don't use that higher maximum rate. Whatever you get is fine.
Hey, Nino, before we move on from that, I know there's several people actually have expressed interest in not populating the USB socket and just looking at using that TTL interface under there. I wonder if you could just give a couple of minutes on just that specific feature.
Yeah, roll on back to the bare board, Nino, and show them the pinout.
All right, let's see if I can do this.
You can click on the, there you go.
Okay. Wow, hello. Sorry. There we go. Underneath the footprint for the USB bridge, you'll see J5, intentionally hidden by the USB bridge when it's installed because it's wired directly to driven pins. But you have ground, TXD, RXD, and plus 5 volts. So the ground and plus 5 volts, that is the power supply to the TNC. That's where you'll connect the supply to the TNC. It'll go into the voltage regulator. There's a tank capacitor on the supply side and on the filtered side.
Quick question. If you plug USB into J3 and U4 is not populated, it will take the DC and ground off of J3.
Yes,
so, and the other thing is that if U4 is populated, don't use the TXD, RXD on J5. even from the bottom of the board. The whole reason for covering up this J5 when the USB chip is there is so that you avoid having the conflicting voltages, bug the U4 chip.
Right. Good points. Other than that, just TTL level data, the consideration is whatever you're driving those pins with should be close to 3.6 volts. I would have to check the data sheet of the PIC to see if those pins are connected to 5-volt tolerant inputs. I don't know the answer to that. That's something I can throw down for next time. But I think a Raspberry Pi is 3.3 volts or 3.6 volts or something. Okay. And I'm gonna zoom in on the schematic to continue that conversation. So here we go. J5 connects to these two lines here, and I put arrows on these schematic wires for myself. So I know when I say RXD on the PCB at J5, I'm saying that's where an external signal is received by the TNC, right? So the TNC is receiving their serial data, and the TNC is transmitting on the pin that says TXD in J5. Have I confused everyone with that?
Yeah, arrows help.
It's these, it's the simple errors that make things not work.
That actually looks really painless to run without the USB chip.
Yeah, it'll work just fine. The whole spacing of the TNC is the same as a Raspberry Pi. So you could stand it on standoffs on top of a Raspberry Pi and wire it directly to the 40-pin header serial port, if that was what you wanted to do.
Yeah, Mike asked a question. The serial pins are the same voltage as the power supply for the NinoTNC. It's the regulator is 3.6 volts in the more recent bill of materials. So the 3.3 volts will still work, but you can expect the PIC to drive the output at 3.6 volts. So you need to make sure, and it's very unlikely the device you're driving will not be tolerant to 3.6, but that's what's going on is the DS PIC will put out whatever the power supply rail is for its transmit data.
I was going to just piggyback some level shifters on there, just because even at 3.6 versus 3.3, I was just going to be careful with mine.
That's
great.
Great.
That I don't know. I think that may be necessary, but that's not going to hurt.
Yeah, right.
Yeah, well, the problem I've got is I'm probably going to run it on an 80s micro that I'm not entirely sure what voltage comes out of it at any given time anyway. It's more to protect the TNC, if you see what I mean.
Yeah,
that sounds fun. Okay. Let's see here. We're still in assembly, adding more capacitors. So you see Tad's integrated test in the assembly. So I recommend, and he recommends, you follow the test procedure in sequence with the assembly, right? So you're doing some significant testing before you've put all the parts into the TNC, is the point there. Because you can. Then he goes into this description of the loopback test. And essentially, you're proving that the audio output and input analog circuits are working, and that the DS PIC is modulating and demodulating, encoding and decoding all the data. And if you have your USB port connected to a host and you're watching a terminal program, you'll even see a test packet transmitted across the USB onto a terminal program to prove that your USB connection is working. Here's a demo. I don't know what this is going to look like over the Zoom link, but we'll give it a try.
I want to talk about the...
Actually, I'll just pause this. It's 8 minutes long. You guys can go watch that if you want.
That feature though is really good, because when I built mine, when it works and you see it come out the USB port, you're like, yeah.
Great. Some discussion on interfacing, finding your USB port on different platforms. I use a Mac laptop half the time. I use a Linux desktop half the time, and I use a Windows laptop half the time for 150% of the time. So it works on all of them. I hope it works on Commodore and Amiga too someday.
Okay. No automatic USB discovery on the Commodore 64.
Not yet. Okay, what else? We've been here for an hour and 20 minutes.
I don't know. I could talk about some of our discoveries with regards to packet radio linking and so on.
Yeah, I think that'd be useful because I think, Tom, one of your questions early on to me was, some ideas for where packet could go.
Yeah, exactly that. Some applications, really. We've got an inspired group of capable individuals in a big organized team here.
I'm really excited about
that. Show the way.
Yeah, and I'll offer, before I transition it to Tad, and I'll hand it off to Tad, and I'll mute my mic. I will just say that this is, for me, a hobby. It's trying to push off the Alzheimer's, and I just love everything about making it work, right? And so that's my specialty, and Tad has been extremely helpful in making this a product that people can use and has a purpose. And so that's why it has the Tarpon logo on it, because he's got a vision for what packet radio can be, that he's making work in North Carolina, and it's growing. So I'll hand it to Tad for his description of the Tarpon network and the way forward with that, Tad.
Just before we move on, Nino, thank you very much for that.
Yeah,
so far. It's been absolutely superb content. Thank you.
You're welcome. Let's see. I'm going to see if I can turn off my screen share and mute some stuff.
Okay, it looks like I'm sharing now, right? Everybody can see my screen?
Yeah, we got the Tarpon screen.
So this is the chat on the North Carolina packet network. The network is a G8BPQ network, and this is the list of the nodes on the network. We've been pretty successful in making a pretty fair sized network. It's about 70 miles wide. And this is pretty much what it looks like. And now the map with a geographic presentation like this has some significant limitations because the nodes in some communities are way too close to each other, and the nodes in other communities are way too far apart. The blue lines represent 2-meter links. The red lines are 440, and the very few orange mustard colored lines are 6 meters. We have had 220 and 900 megahertz links in the past, and for various reasons, there aren't any now. There will be again in the future. We have 6 900 megahertz 10-watt radios around which can be applied. So this is all on Google Earth. If I zoom in, you can see there's a bunch more stations in various places. The chat network runs over this. Now that's our primary app is chat.
Tad,
yes,
what sort of distances are we looking at there?
So the whole network is 70 miles wide. Let's see if I can, my Google Earth is buried here. Yeah. So the header for the chat, the zoom is over top of my, the displayer. So that's 12 miles, that one here between Mike and Larkin. The furthest one I think is on the order of 20. That's 16 and a half. Now these are 2-meter simplex links, and all except one, actually 2, come to think of it, all except 2 are private residences. And the 2 aren't really that great. One of them is on a 2-story office building where I work, so I can have access to the network from my office. And one of them is at the American Legion Hall, which is a clubhouse, and that's down here. And then that's an antenna hanging from a 35-foot branch above the building, and that was because they didn't want to give us a 30-odd foot tower, which would have been really handy. Anyway, so between houses, you don't get that much range. We are in gently rolling hills, which just get in the way, and heavy trees. Okay, so anyway, the network, the way we're building it, is all of our links are dedicated point to point. So if you, in this, for example, in this case, at Mark's house, he's got two 2-meter links, and they're on 2 different frequencies spread out by 3 megahertz. There's no rules in the United States that prohibit 24/7 automatic operation on 2 meters or 440, and we can run multiple radios simultaneously from the same site, so long as they're transmitting different information. So we can take a message in on one link and immediately put it back out on another through the G8BPQ stack. Now we're using G8BPQ, and our network is implemented the way it is, or where it is, I should say, because we haven't gotten as far in the project as we want. The G8BPQ will eventually be replaced by our own stack, and it just depends on volunteers to complete that work. The link, sometimes we have no redundancy, and because we're splitting frequencies all over the place, it's possible for a critical node to go out and disconnect some people, and that happens periodically, and we have to go and figure out what went wrong. Usually the person that lives at the house can take action and fix the problem. So house to house to house actually comes an advantage there. The reason why we're using dedicated point-to-point links, even though it requires more transceivers, and actually let me switch pictures here. I'm going to go back to the Tarpon webpage, and that actually is the picture I want. This is this is what I want right there. Doink. Enlarge, please. Nope. Go back. I think I'm sucking up all my office's bandwidth by being on the Zoom. Anyway, that is a 4-port packet node. And you can see 2 radios on 2 meters, 144.31, 147.585. And there's 2 radios on UHF down at the bottom. And they're all running, other than 1200 baud, all using NinoTNCs, and you can see there's 4 of them. Now, the reason why we run radios on disparate frequencies and use dedicated pairs to make a link is that you don't have to wait for the channel to be clear. Your P persistence can be set way up. Your TX delays and frac times can be calculated to work out, so you don't wait. If you listen on the channel, there's no empty spots until the data has passed. If you had, for example, 10 stations on 10 sites with 1 radio each, your throughput is divided between all of those stations. Plus, you have a very high chance of collisions because of hidden transmitters. If you were instead to break the network up into separate links, you'd end up with at least 9 point-to-point links with a total of 18 radios, but you'd never have to divide your channel occupancy. You could basically use all of the bits that you have. Now, on a 1200 baud link, the throughput that we get, actual real throughput, is about 25 characters of application data per second across the link, which isn't anywhere near 1200 bits per second, but there's a lot of overhead. Not only the TX, RX, TX switching, but also there's an acknowledgement cycle that takes up time. So if you're transmitting, for example, 120 bytes across a link, before the channel is clear, you've probably used 3.5 seconds at 1200 baud. Now, the interesting thing is our killer app is chat. Now, when you're watching a chat, let's put it back there for a second. You're occupied reading. You're not bored so long as there's text coming in. The text flowing at 25 characters per second will get you another line of chat text every 3 seconds. So if you were to saturate your 1200 baud links, you'd be very busy keeping up with the chat. If you ran the thing at 9600, of course, you could get much faster. Now, the chief advantage of 9600 for us is lower latency. with the Tate radios are so quick at switching. The TX delays are being set and below on the order of 20 milliseconds, whereas a lot of the radios that we've been using on packet traditionally have much higher TX delays. The Alinco DR135 is on the order of 400 milliseconds. So if you run 1200, hey, even 9600 on an Alinco with that kind of a TX RX switching delay, you might as well be running 1200 baud on a faster radio. So anyway, our goal here is to make this whole network fast, or not fast, but usably fast, and reliable. We don't ever get retry failures because of congestion, because we don't have any collisions. So what's the advantage of running 9600 baud at all if we only need 25 characters per second to keep the chat users occupied? Well, obviously there's other users. If you write an application that, for example, goes and scours all the weather terminals across the network and displays a map, you're going to want to get that data relatively often. With 30 stations reporting, you could imagine some amount of bandwidth consumption. There's lots of things you can do with the packet network that stays up all the time. Okay, so questions right off. Any, you can verbally. I'm not watching the chat because I'm on the.
Yeah, there's been a few in the chat which Nino's been doing a good job of hoovering up, I think.
Okay.
One from Dave, which looks interesting. This sounds like KA9Q and NOS networks. Would you tend to agree?
We're using G8 BPQ, their entire stack. We have the BBS, we have the chat installed in every single node. The NOS. It may, things have changed a lot since I got into packet radio. The advantage of running various people's protocols across AX25, generally speaking, does not include improvements in throughput. Correct me if I'm wrong, but so far the most successful app has been the chat, mostly because it's extremely social and everybody gets to meet everybody. Everybody on the network has internet. And we can presume that if we go and say, for example, hey, there's this picture on this website, come and look at it. Like here, there's a KMZ file that was tossed around. There's other examples of people posting links on here. We can assume that the people will have access to the internet so they can get that. We don't have to send that traffic over our network. We'd like to be able to, but it hasn't been necessary to attract new participants. And that's been one of our serious problems. When we got into this network business here in North Carolina, there was no packet to speak of, excepting for last mile to the internet projects like WinLink and APRS. There wasn't anybody building a packet network that could relay more than one hop away. So station through digipeater to station, or station through node to station, that was as far as it went. And the people who put together to make NC Packet happen wanted a network because they're a lot of fun. So we set out a few rules to try to describe what we'd like people to think of when they're building onto this network. And one of them was, we want it to be ham radio exclusive. So let's see what happens if we don't have any internet. We want this thing to never be routing traffic over the internet at all. And furthermore, we want everybody who's using the network to actually be using ham radio to get to it. So that was rule number one. And that actually excludes a lot of traffic, but it makes it something that people desperately want to do in order to see what's going on our network. The only way you get to play is if you have a connection to the network. Of course, if someone's 100 miles away from the closest approach to the network, it's a problem, but it's a solvable one. It just takes 5 more stations in between, or more likely 20 to go 100 miles, because they're not all in a straight line. They're not easy. You can't just say, well, I'm going to use this national park to put something on top of their mountain. People might look at us funny. So anyway, the goal of the project is to get more people in the project, which is kind of self-serving, I guess. Yeah, and the other thing about the RF only principle is that it attracts people who wouldn't pay any attention to us if we didn't do it this way. We lose people for sure. Absolutely. You all in Europe cannot, in England, cannot get to our network. And it's just kind of a sorry thing to think about. It's like all these people that would love to play with it, but you can build your own. It's a different conversation when you're talking to someone that's 100 miles away than someone that's thousands of miles away. If you're 100 miles away, we could actually do something about that with a lot of effort. Yeah, going through the satellite would be fantastic. I don't think we'll be able to do chat through it because I don't think anybody would like us to be consuming the bandwidth indefinitely. But yeah, we do need to have a geosynchronous satellite here. I'm waiting for SpaceX to get their Starship going so we can piggyback a satellite. I saw that a middle school put their own satellite up. Anyway, distracting. Okay, what else is going on? So we have dedicated point-to-point links. We have no internet, and we attract people to the project. Chat is very common and very popular. One of the things we did, which is kind of neat, is that since everybody's running a G8 BPQ node with their own chat application, rather than having the people connect to chat as if they're users on the channel, everybody connects to chat as if they're the sysop of the chat. Now, only one person is uplinked into the chat, and everybody else comes through the network. And what we do is we connect the chats to each other. So if you have a network, for example, let me go back to this page. Clear that out. I don't need measurements anymore. All right. So if Sky, for example, Sky and Larkin are father and son. They're on the same. They actually have two separate Raspberry Pis connected with a wire link, and then Larkin connects to Mark. Mark connects to Michael on a different frequency. If you were at Larkin's house and you type something into chat, the chat node at Larkin spits it back out to all the users, which is none, just Larkin. And then Larkin sends to a copy of that from server to server to Mark. Mark's node then puts it out on Mark's terminal and sends a copy of it down to Adro and over to Michael at two separate links simultaneously, on two different channels, and they both get a copy of it. Michael then puts it on Michael's terminal, and Adro would put it on Adro's terminal, excepting he actually doesn't live there. It's a relative's house. The bottom line, though, is that at no point does a chat line get sent over a link twice. Now, if you used BPQ chat the way most people do, everybody's coming in on one frequency into the server. And when one person types a chat line, it gets transmitted out over the server to 5 or 6 different stations on the same channel. And all of them have to acknowledge it before basically you can move on. You're basically creating a choke point. We can get 30 people typing on chat, and they can type as fast as they want because they still can't keep up with 25 characters per second overall. And the other interesting thing is if you had 1,500 people on your chat network deployed the way we're doing it, what you're going to end up with is the latency is going to scale up. If you think about it, if you had 1,500 people in a line and you're taking 3 seconds to send 80 characters across each hop, that's going to be 4,500 seconds. So an hour and a half later, you'll get chat to the other end of the network. Of course, with 1,500 people, you wouldn't have them all in a straight line. They'd be a bunch of stars of stars. And so it wouldn't be so bad. But the really important part is, if you think about it, if they're all typing, you'd saturate the network. Okay, the chat's going to flow faster and you're going to be able to read it. Most people don't do that. If they sit there and look at a chat screen and it's busy as all heck, they sit there and they try to catch up and read. This chat is self-limiting because of this. If everybody was on the same chat channel, which, I mean, obviously you can have multiple chat channels and that's a different discussion. But if everybody's on the same chat channel, the more people you add, it doesn't do anything. It doesn't change anything in terms of the behavior because you only have one copy of each typed line going across each link. So this thing is fully scalable. Now, if you do run multiple services or multiple channels on chat, now the throughput on each link is starting to become important. You could, for example, break up the country into 50 different chat channels where each chat is going to be, every single chat is going to be spread throughout the entire network. That's going to create a bandwidth limit, or you're going to hit a bandwidth limit, and you're going to need something higher performance. Now, the reason why we're running VHF UHF packet here in North Carolina instead of running on Wi-Fi channels or Wi-Fi technology is because the length, the distance you can go house to house on Wi-Fi is considerably shorter than you can do on 2 meters. You really have to have towers. In fact, you have to have very big towers. A 1,200 foot tall, what's that? Call it 400 meters. 400 meter tall tower has a range of about 8 miles in our neighborhood to a house. A tower to tower links, you can go probably 100 miles. And so the network from tower to tower, if you could get permission or buy access to the tower to put your station up, you could have a statewide network with 40 towers and back tops across our entire state. Our North Carolina is 550 miles wide and has a population of about 10 million. There's a lot of TV towers. It could be done, but you'd have still have a problem getting to everybody's houses. You have to break it down into 440 or 900 megahertz or something. It's not as trivial as handing this Tarpon strategy or recipe over to a ham. Your chances of success of getting the system implemented, say if you sent 20 boxes to some far removed place and said, here, set up this network, your chances of success with a 2 meter and 440 network is much better than for UHF. So yeah, the trick is to promote. That actually is if you look at all of the skills necessary to build a packet network, the one skill that is most dear is a promoter, someone that can actually talk it up and actually you're going to walk someone through the process of becoming new to the network. So I could go very long, just like Nino said, this could get very long. So one of the things our project is doing, which successfully, I think, is attracting new products. So new software, new hardware. And we're trying to make it so that we are an environment where someone who builds something new or writes a new software will get the software and the hardware tested. You're participating in a large group that's eager for your product. And as a consequence, and as we get bigger, we'll get more products. And there's lots of ways to improve packet radio if packet radio networks, terrestrial packet radio networks, are what you're about. There's an enormous amount of improvement that can be done. And the Tarpon organization was founded for terrestrial amateur radio packet networks. Not to say that we wouldn't want to deal with, Martian networks or for that matter, Earth to orbit to Earth would be spectacular. Let's see. Any questions that are cogent to hear? There's a lot of commentary that's outside of my ken, but yes, go ahead.
The chat has really taken off. I think you've sort of given people a little bit of a spark here. It's great. There's talk going on in the background of how, not just that we should build this network, but how to do so, which is fantastic. It's day one, so thank you. Yeah, satellites keep coming up. It's an interesting one. So in the Tarpon architecture, do you have sort of support for transient links that might just be there for, I don't know, 3 minutes a day, that kind of thing, to transfer transfer data around asynchronously? Obviously, that doesn't work in a chat scenario, but for something like a mail scenario, perhaps.
Yeah. So if you had someone that wanted to do it, all of the servers have the BBS program installed and mostly they're configured. So you can drop a message as a bulletin and it will fan out through the network pretty rapidly. And mostly they also have the ability to send to an individual participant. It's not the first thing that people configure when they get the thing going. So that is a problem. But if one of those participants said, okay, look, I've got this equipment that will talk to the International Space Station for once or twice a day, I will look for incoming connects. Anybody on the ISS, hey, if you want to send an email traffic into our network or get one from our network, will be available. And someone, for example, in Europe could say, well, hey, we should be able to get something through the ISS to this North American network once in a while, or whatever, Iceland or Colorado or any place. It could be done. It's just a matter of the participants have to get together on it. The one thing we don't want to do is cheat. We don't want to take traffic through the internet. And we don't want to talk to anybody who would forward traffic that they got through the internet. Now, that's not, I mean, strictly speaking, that doesn't hurt us, right? If someone types a piece of message and says, hey, put this on the Tarpon network, that's not a problem. In fact, our rules specifically say, if you want to hand copy something from your PC to your Raspberry Pi or whatever and put it on the BBS, that's fine. What we don't want is to pretend that we have a link that goes from point A to point B that isn't on ham radio. In other words, nothing transparent. It's got to be manually or hand carried at some point to copy and paste.
So I kind of touched on this in a message a few minutes ago in the chat. See, BPQ itself has got the concept of AXIP links. So
right.
So ignore the internet, take the internet out. I mean, in Europe, for example, mainland continental Europe, there's an enormous ham WAN, 2.45 gigahertz.
Yes, and that would be
area network.
Yes.
So I mean, I can see there being interest in our community around building kind of a hybrid network where some parts might be over AX25,
absolutely.
Some parts might be over ham WAN. So is AXIP sort of still exposed in Tarpon?
It's not, but it wouldn't take much to change it.
Cool. So it's not sort of all locked down.
Yeah, no, it's not. There's nothing that's saying you can't do it. It's just that there's nothing right now. The majority of the participants, possibly all of them in our North Carolina network, use the automation to start up the node. And we have a really trivial, let me actually share this. I'm going to share my screen again. And I'll show you what this looks like. So you're seeing my screen?
Sure.
Okay, so let me go and bring this a little bigger. So this is our config file. And this is what feeds the BPQ system. So forgetting all this stuff because it's not being used. This stuff here is pretty much what you have to put in to the program in order to get your Tarpon node to start. Now, this part right here turns into the info text that GAPPQ gives you when you type info. You have a node named BBS call sign BBS. The BBS name is BBS, by the way. Every node has a BBS and they're all called BBS and they don't propagate. So if you want to get to the BBS at K1TR's node, you connect to K1TR's node and then type BBS. And the forwarding system does that as well if you look at any forward script. So this is really trivial. The lat-lon, by the way, gets shoved into a couple of messages. We have a, let me see if I can show you this. If I run this, yeah, I know. All right, so I'm on Qt term now. If I type, I'm actually connected to the TAD node, which is my node at my house, and you can see the traffic attempting to go through. Why aren't we going through? It's a Steve Jobs moment. As soon as you do anything, the network will die. Anyway, I have a command called tinfo, which just calls a port number on the local host, and it gives you information. One of the things it gives you is the lat-lon that came out of the node.ini file. This basically just goes through the elements of the status of the network and lets you see what's going on. One of the things it gives you eventually is the voltage. It was actually it's the undervolt reports if you've had any on the Raspberry Pi, because that leads to SD card corruption. So we put that into a place you can get it. So that let's see if I can change this. There's some things that aren't working right now, and I'm blaming the Zoom chat. Yeah, so this is basically a breakdown of the node at my house. Undervolt events found in the file is none. This right here, this piece of information is completely useless for Packet, because that doesn't help you, excepting that maybe a fifth of the people in our Packet network really aren't that familiar or comfortable with playing around with routers and switches. And periodically you'll find someone on the repeater saying, hey, my node seems to be working. I can tell from the blinky lights, but I can't get into it because I don't know what the IP address is. because they're running Wi-Fi from the Raspberry Pi, and maybe they did something to their router to change things. And so you can connect over to their node and pull down the information they need to reconnect to their node. Anyway, sorry, I got sideways here. Did I answer the question before I got sideways?
Yeah, I think so. Thank you. Yeah, it's yeah,
it's
just seeing
the node.ini file, and can you use AXIP? Right now, the node.ini file is the primary method that people use to configure their node, and there's nothing in there about AXIP. It wouldn't take a lot to put something in there. It's kind of neat to have it so it's not, only because you can really prove and show really rapidly that we are not dependent on the internet for our traffic. But we'll come up with another way. If we have a real ham WAN here, or Arden mesh or whatever we get, that will definitely become part of this. And I would, in fact, I really would love to have that at my house. I actually tried to start a group locally to fund a tower mounted system. We had an offer for a 600-foot location on a TV tower in the south side of Raleigh. It's about 15 miles from my house. Unfortunately, it would also be outside of my range on 2.4 gigahertz. But I had in mind that if we could just get that thing up there, we'd figure out how to relay. And what we needed is $150 per participant in our original. Is anybody interested in this? We had a bunch of people, and when we divided out the cost of the thing, it was going to cost everybody $150 just for the base station, and then whatever they needed to talk to it, which in some cases was practically nothing. I still have boxes of little cheap routers hanging around. There's so many of them littering. Whoops, that one's plugged in still. Hang on a sec. Yeah, I have so many of them littering, because I'm still screwing around with those things. Anyway, yeah, I'm a fan of ham WAN, not necessarily ham WAN, but the whole notion of doing Wi-Fi comms. Some of the Wi-Fi comms networks have given up on Part 97 ham rules and have switched to Part 15 commercial non-licensed rules, because then they can connect to the internet and draw down web pages and what all without violating Part 97. They lose the ability to run high power, but they weren't interested in that anyway, I guess. So I'm a little discouraged by that. I'd prefer to do it in ham radio rules. I don't know. What do you all think?
I think for me, seeing the Arden stuff, it just seems to go hand in hand with this, and certainly finding something that takes you've got the capabilities of Arden's bandwidth, but with the tiny the tiny bandwidth requirements from the chat that clearly is the killer app in this.
Oh yeah,
finding a way of usefully interoperating is brilliant.
Well, there's people that will not be able to reach the Arden system that are on our network, and there's people that can. The people that can reach it are going to hear about it all the time. The people that can't will have this as a niggling thing that, how do I pull this off? And I think that would be good for us, just because it's really a lot of fun, and it can't possibly be bad for us to have an Arden link into our house, right? I would love to have that. So anyway,
Tad, we're coming up to the top of the hour. I just want to give, there's a few people who probably just wanted to come off, who didn't want to necessarily be on the recording or whatever. So I'm going to go ahead and just thank you both, actually, Nino and Tad, for your time. this evening. Absolutely fantastic talk from you both. It's nice that it's not been too like formal and you're not just taking us through PowerPoint slides, but really sort of showing it hands-on. It's great. It's exactly what I think is most valuable for us here. So thank you very much. So yeah, nice. Thank you. What I'll do is I will stop the recording now, and then if anyone wants to come up, maybe just have a little bit more of an informal chat session, those who are left, and go from there, really. How's that sound?
Sounds good to me.
Cool. Yeah, I'm not sure, 2 hours in, not sure how long we'll go for.
I actually have it's coming up on 5 o'clock Eastern time here, and actually I'm the host of a ham radio club meeting that's starting in an hour. About 20 minutes.
Give you somewhat of a break then. But thank you very much from the online amateur radio community. Really
any questions? By the way, if anybody wants to engage me back, I realize I talk too much, but if anybody wants me back in this, I'm perfectly happy with coming in another day as well. Or
cool.
We could do a Zoom directly without the club. Send me an email. I posted my email address is tad@mac.com, and I'm on QRZ. And if anybody wants to just get on a Zoom independently to talk about things, I'm fine with that too.
Yeah, appreciate that very much. All right, let's get this recording stopped.